Hello, everyone. Didn't expect so many faces, but this is great. So I'm a PhD student, as Dr. Billinghurst said, and I work in the sketch recognition lab at Texas A&M. And I'm not going to talk about my sketch-based applications today, but if any of you are interested in those, I have lots of demos and I can show you those PowerPoints as well. I'm going to kind of focus on the mobile systems that we've developed for team coordination and support, and they kind of span into different areas. So I'm going to give an overview of all the areas and then kind of dive into my focus area. All right, so as I mentioned, we're researching and developing applications, mobile applications for users, and we're focusing on users that work or operate in high-stress environments. And we define that as users that have a heavy cognitive load. And that's a load related to the control of your active working memory. So the groups that we work with, usually their main task is navigation, coordination, or assembly. And in teams working in hazardous situations, these tend to be very critical tasks. So in those situations, effective human-to-human interaction can become impaired and very, very difficult. I mean, even in normal everyday situations, it can be a challenge sometimes. So this is kind of the work that we're focusing on, is identifying the user state, and we're doing that in various ways. One way we're trying to do this is to identify gesture recognition. And we've done some previous work using the Power Glove. I don't know if you guys are familiar with this. It's basically a glove that has a bunch of motion sensors on it. And we've used that to identify interaction or object detection, or do object interaction detection, in an office setting. And we've used that to be able to deliver that information to other people in an office, so that, for instance, I'm working at my computer and I decide to make a phone call, nobody just pops by and interrupts me and starts talking to me before they see the phone. That's always kind of an awkward situation. So we've developed a system that would do automatic object interaction detection and then alert other users, okay, this person is typing, or this person is on the phone, or in various other activities, to be able to create that kind of awareness between coworkers. And that paper is published in the International Journal of Studies. So another area that we've been exploring is identifying and classifying physiological signals. So the motivation behind that is we want to be able to allow team members to be able to keep an overall status of their teammates when verbal communication is not possible. And we're also using this information to be able to identify early signs of post-traumatic stress disorder, or even just an overall stress state, to be able to allow teammates to kind of mitigate that and step in when there's a crisis. We're also exploring applications in communication. For instance, one of my colleagues is exploring social skills, the development of social skills, and in particular focusing on conditions like Asperger's syndrome, and where a person has difficulty identifying facial cues or bodily cues that can help most people identify somebody's emotional state when they're interacting with them. So having that information given to them in a visual cue is probably more easier and can help them to develop social skills using those visual cues. And then in addition, we're focusing on exercising, creating exercises that will help people to learn empathy and possibly help with conflict resolution. So for instance, if I'm in a group and I'm mediating a group, we're trying to explore whether or not being able to see how a person is reacting to things that you're saying, or topics that you're bringing up, can help a group to work better together and communicate better. So another motivation is, of course, sports and entertainment. And we were trying to determine, if you're an audience and you're watching some sporting event on television, how interesting would it be to be able to know how the players or subjects of the program that you're watching are feeling. And I just recently attended a CRI conference in Austin, and there was actually a guy that simulated a ghost hunting show that did a similar thing, and he kind of evaluated the audience on how much they enjoyed the show based on whether or not they could see the people's reaction to fear given the situation that they were in. So it's very interesting work. I can reference a link to that paper if you're interested in that as well. But that's another area that we're exploring. So the consideration with this research is that one, emotions are personal, so privacy becomes a very big issue when you're developing applications that deal with that. And then also our reactions to different stimuli are going to differ. So just because I find something funny, it might not necessarily be the same case for everybody else. So in order to kind of explore how we can pretty much elicit certain responses in order to be able to classify them, we conducted some preliminary tests using EEG data, which is a headset that my colleague is wearing. You guys see that? Okay. Okay. So he's wearing an EEG headset, and we monitored him, and we forced him. It was kind of mild torture. We forced him to watch Fox News programs in order to get his blood pressure up, and that was very, very interesting. He was very irritable by the end of that month. But so we tried different types of programming, limited to about 2-minute video clips, and in order to get kind of a user-dependent data visualization of the type of data that we can collect and determine whether or not there was a discriminatory factor between states that we were trying to induce. So using that information, we decided to proceed and do a real study using, instead of video images, we used images from the International Effective Picture System. And basically that's a large database of images that lots of people have rated on their reaction and their intensity. And you can use this information to basically try to elicit certain reactions based on a large majority of people that have rated them, and then try to elicit a response based on the level of intensity that other people have assigned to them. And so we connected the participants to a biosensor pack in addition to the BCI headset. And using 8 participants, we showed them about 50 images, and we wanted to classify the smallest time interval possible because we want this to eventually apply this in real-time systems. So we only collected about 5 seconds of data. So we showed them the image, collected the data, and then moved on to the next image. So with the user study, like I said, we had 8 participants, 50 samples, 20 signals. Then we calculated 14 features per signal, which resulted in a really gigantic feature vector and a lot of data that we had to kind of process. Very fun. And so we performed the same tests using both user-dependent and user-independent testing. And then we used forward feature selection to identify the significant features in all of the data. And surprisingly, some of the features that we identify or that we used from the data are features that we use in sketch recognition. So that was kind of an interesting find. The feature that kept appearing was the normalized distance between direction extremes. Basically the distance between the highs and lows of the signals that we currently use to help us identify changes in a stroke. We use the same thing to identify changes in the T7 sensors in our EEG headset. So that was kind of an interesting find that came out of our studies. And then we also performed user-dependent testing, which we kind of figured that would be more beneficial because, like I said, all of our reactions are different. So with the user-dependent testing, we produce about an average of 50% accuracy on six emotions, which is higher than chance, but it's still not where we want it to be. But the positive thing is that in some cases we got up to 60% accuracy using only one sensor. So that's ongoing research. We're trying to move toward increasing mobility by using less sensors, but being able to identify as many user states as possible. Right now we're focusing on just a stress, non-stress state. It's a lot easier since you only have 2 states, but eventually identifying emotions is kind of a long distance goal, but it's a goal of ours. So another area that we're exploring is gathering and using environmental data to be able to identify a person's user state. And one particular application that we've been developing that's kind of my focus area is an application called GeoTrooper. And it's an application that helps paratroopers to locate their rendezvous points after jumping out of an airplane. So a paratrooper's main job is to conduct airborne operations. So their main task is to pretty much jump out of a plane and assemble as quickly as possible in situations where there's low light and no light. And I think the sound out of this video is probably not in show you. So we spent about we spent about 9 months going back and forth to Fort Bragg in North Carolina, which is kind of the basis of the airborne squad, and we did pretty much a large ethnographic study where we, kind of got to know these guys, learn about their jobs, learn about the tasks and the dangers they face, and see if we could find a system that helped them complete their jobs basically quickly and safely. Now, keep in mind that you're doing a practice jump during the day, but when they would do this, it'd be completely pitch black. They wouldn't be able to see anything. They kind of have to go off of coordinates. And the guy in the upper right, I don't know if you can see that it's really not in Chicago, but they carry usually up to 200 pounds of equipment. Yeah, I wrote that on there. 91 kilograms of equipment. So they could weigh up to 400 pounds or like 90 pounds. And at the same time, they're probably fatigued. They haven't slept in many hours. They've been on this plane the whole time, and there are very real security threats. When they jump out of the plane and they hit the ground, basically they have a limited amount of time because I don't know. I'll show a picture of that, but there are lots of them. I mean, if you see 1,000 guys jumping out of a plane, it's no secret. So people are already trying to get to their location, so they have very limited time. And then at the same time, they can't see and they can't talk with each other. So pretty much, he hits the ground. It's not a soft landing. Kind of disoriented. And his main job is he has to look up as quickly as possible and find out which way the aircraft is going, and use that as an orientation. This is current practice. So once he's done that, he basically has to look for a giant flag, or it's called a steinerate, and it's basically an infrared chemical light that's mounted on a 15-foot pole. And if he can't see that, then he has to run around until he can find it. And during that entire time, he's in danger, pretty much. So assemblies with trained troops of soldiers can take about 20 minutes or even hours if they get lost. And people have gotten lost even in training situations on the practice drop zone where they know the terrain. So in unfamiliar terrain, it can be a very, very real danger. So our solution, our task, was to create a location-aware system that was portable and lightweight, and we wanted to use commercial off-the-shelf components because those tend to be cheaper. We created a system that generates an ad hoc Wi-Fi network, and it broadcasts and receives encrypted GPS coordinates of the locations where they need to rendezvous. And then it offers multiple views that give different levels of navigation. So the hardware components that we use, most of them we bought pretty much online. The beacons that we created consisted of these small ruggedized computers that could be attached to pretty much any equipment that they wanted to orient themselves to once the equipment was dropped off of the plane prior to the soldiers. And it included a Wi-Fi antenna and then an amplifier that would boost the Wi-Fi signal if it was required, and a GPS component. And then for the receiver, we just use Android phones as our platform. The receivers were given to the soldiers and help them orient themselves to the beacon. So the way it worked is basically they would attach these ruggedized computers to a tank or their equipment, anything that needed to that they needed in order to complete their mission. They would push them out of the planes before the soldiers would jump, and once they hit the ground, well, before they pushed them out of the plane, sorry, they would turn on the beacon system and set a timer. Basically, they could identify how long they wanted the beacon to sleep or delay before broadcasting its location, or based on the impact the beacon could start once the equipment hit the ground. So basically, they would set up the timer. They would push the equipment out of the plane. Once the equipment hit the ground, it would start broadcasting. And then once the soldiers landed on the ground, all they would have to do is pull out their Android phones, basically turn on the application, and the application would search for a specific SSID. Now, keep in mind these beacons weren't always constantly on. They're actually doing a beaconing action, so it would broadcast for about 5 to 10 seconds, and then it would shut off. And then once the Android application picked up on a specific SSID, it would decrypt it. If it contained the identifier that was unique to our system, it would decrypt the GPS information and then point the soldiers to where they needed to go. And then we created various different interfaces based on feedback that we got from the users. One interface was just basically a number that identified how far away they were to the closest beacon, whichever beacon they wanted to select. Another view just showed an arrow so that the soldier could look down, see an arrow, and keep running. He wouldn't have to keep watching the screen, basically. Another view is based on the methods that they're currently using, which just has a compass and then gives information about distance. And then even another view provides more information that provides them with a military grid reference system, which is currently not available commercially, but it shows them all the beacons in their area so they can decide, if the situation calls for it, I'm just going to go to the closest one rather than the one I was assigned to. And then to limit light pollution, we provided an interface that could only be seen using night vision goggles as well. So we conducted a field test with about 50 soldiers, and we placed beacons in various areas on that giant drop zone that they were, I think it's called Sicily drop zone, that they were dropping into to do their tests, and we didn't assign any markers to them so they couldn't see where these beacons are. And we asked them to locate as many beacons as possible. And we were surprised to find that every participant navigated to all assembly points in 25 minutes or less. And they weren't even running. They were just pretty much kind of walking nonchalantly, which they wouldn't do in a real life situation. But given the fact that it took them only 8 minutes average to walk to each beacon, and a trained team takes about 20 minutes to assemble in the field, that's really, really promising. And so after the test, we asked them to rate the usability and the effectiveness of the system. We had one guy that had a little trouble with the system, but for the most part, you can see on the average that everybody rated it fairly high. And we got really great user comments. My advisor decided to do some requirements gathering. I stayed on the ground. Yeah, it was a really great time. The guys were great and they were very helpful. So overall, we feel like the demo and the testing was a success. So how does this kind of tie into all of the work that we're doing now? So currently, now that we have a fairly stable system, we've been approached by other groups that work in similar areas. For instance, firefighters or disaster relief workers, and in a sense, these groups present even more of a challenge because not only do they have limited visibility as well, but they have an even shorter time window in order to perform their jobs. And there are lots more challenges. I mean, not only are specifically for firefighters, not only are the situations critical, but there is a potential damage to the equipment as well from the fire threat. So I found a really good video that kind of summarizes the difficulties in particular that firefighters have. Near Texas A&M, we have this giant field, we call it Disaster City. And basically, firefighters come from all over the world to train at this facility. And not only does it have, giant buildings that are crumbled and all kinds of situations that they can simulate to train these soldiers, it presents us with a great opportunity to go out and see how they work, which is much nicer than having to get on a plane every couple of months to go to North Carolina. So this is pretty much in our backyard, and it's very nice.
Equipment and methods used to help the firefighters has hardly changed in generations.
When I first came into the fire service, we didn't have trousers. We just had tall boots and then long coats. It still left you to an extent. The hooding. We used to use our ears as ear gauges. If we couldn't take the heat on our ears, it was time to get out. What we learned from our forefathers, we built on. And what we've tried to do is say, what is it that we can do to make our jobs safer, as well as maybe more efficient?
But they're using 19th century techniques in a 21st century world.
We went out and we interviewed a lot of these firefighters, and as far as visibility, I mean, you can kind of see what's going on in the. I mean, you can see the fire, and when the smoke comes on, that's pretty much it. They're blind out there. So we've been exploring different types of interfaces that would help them not only keep an awareness of their teammates, but also keep an awareness of, okay, where's the exit? Because I mean, once you get in a building and you get overwhelmed by smoke, it's kind of hard to keep your bearings about you. So for current work, we're looking into developing an AR interface for our application that will allow soldiers and firefighters and disaster workers to be able to keep their hands free if need be, but also to be able to locate very important points in those disaster situations, whether it be teammates that have stopped moving or teammates that are in a very, very stressed state, higher than what they started at. And then also to identify very significant points, for instance, for firefighters. If they put a beacon outside of the building, then that will help orient them to where they need to go in order to escape a dangerous situation. We're also looking at developing a haptic vest that kind of mirrors the haptic interface that we've already designed for the geotrooper system. And the way it works is, and I can give a demo for anyone that's interested. The way it works is the Android phone will pulse if you're facing toward a beacon, and as you get closer to the beacon, it'll pulse faster. So in those situations, you don't even have to look at the interface if you don't want to. You can just go off of the vibration from the Android phone, and then one of my colleagues is developing a vest that can be worn under the clothes that has the same tactile sensors and will vibrate in a similar manner if you're facing toward the beacon. Excuse me. And then also we're currently exploring the development of an effective interface, basically a stressed and non-stressed state that kind of goes off of your baseline at the beginning of an event that will help your teammates to identify whether or not you need assistance. So those are kind of the current areas that we're researching or looking into. Yep, that was it. So yeah, that was a brief overview of the current research that we're doing. And again, if any of you are interested in our sketch-based application, I'll open it up for questions.
Great. Thanks, Danielle. So here's some questions for Danielle. I've got one to start with the, can you go back to the slide showing the Wi-Fi ruggedized the one showing, well, this will be fine, but so you said that you attached the ruggedized tablet to
oh, you mean the equipment?
This one here, the
okay.
equipment that you pushed on the plane. And
Right.
so when it lands, what's the range of the Wi-Fi antenna?
So one antenna with an amplifier can broadcast at 565 meters. So the way, I didn't mention the daisy chaining of that. So the way the beacon works is not only does it broadcast its own location, but it looks for other beacons in the area. And if it finds another beacon, it'll broadcast its location and then the location of the beacon that's closest to it. So even if a soldier is out of range of the beacon that he's assigned to, the daisy chaining effect will deliver that information to the soldier and pass down the chain.
Because I imagine that when you've got a lot of paratroopers coming out of a plane, potentially they could be spread over a couple of kilometres.
Right.
So if that's the case, then how do they find?
If
Do they have a GPS location where they notice?
Yeah, so they'll put a default location in there that's ideally, if the pilot is doing his job correctly, should be the center of the drop zone. If they overshoot their drop zone for any reason, then most likely all of the soldiers will be out of range, but they can at least rendezvous at one point and then decide, okay, how do we proceed? If everything goes well, usually the way it goes is the equipment goes out first, and it should drop in a line as it's going out, and then the soldiers come out afterward, and then the daisy chaining effect starts, and then the soldiers gravitate to or navigate to the one beacon, and then they can go continue on to the other ones.
Okay.
It's rare that they ever get that far from their equipment.
Any other questions?
Security things that you consider, such as like a encryption and such.
Yeah, so we have our procedures. I mean, we want to, the grant that we were provided doesn't cover security, but we are exploring that because, we like our equipment and we want to use it. If they get compromised, they're supposed to shoot their phone. Of course, the phones were loaned to us by Google. We're like, no, don't shoot the phone. We'll come up with something. So right now, the security measure is if for any reason the GPS coordinates of the phone stop moving a certain amount, basically the soldiers stop moving, which they're not supposed to, then the phone will shut off. It'll lock and it'll shut off. I think that happens after 12 seconds. But yeah, we're looking at other ways to. No, so the Android phone is becoming standard issue of Army. I don't know about the Navy yet, but so pretty much every soldier had their own phone, and they took it with them anyway. So rather than having to take their own phone, that's just going to be.
I heard something recently about the military using softwares to coordinate like strike tests.
And I think firefighters know anymore iPhone, but sorry for you iPhone users, but yeah, we're seeing more trends now that people that are in these high stress situations kind of tend to rely on what little technology they have, even if they don't necessarily use it, even just for using it as a light, which or a flashlight, but if, for instance, that fails, it's like the next thing people go for is like, oh, I have my phone. So I feel safe because I have my phone and the light out on or something. So, yeah, we've been seeing that a lot.
Off the shelf.
They're built by Panasonic, and they're built specifically for military use. So the military already use them currently in their operations. We just said, okay, let's take what they already have rather than add to what they're already carrying. So it was kind of as we were doing our studies and talking to these soldiers, they already have Android phones on them. They already have to carry these ruggedized computers. What else can we add to that to make this system? So, rather than build something for them to carry.
They look very much like a tablet when they have similar.
Yeah, it's a touchscreen tablet. Don't by reference. Sorry, are there any other questions on the
In this case, find that the soldiers have on a purely just a receiver that doesn't actually transmit back to the beacon.
It doesn't communicate with the beacon, but the phone will communicate it with the other. So if you were in range of a teammate, it doesn't tell you any information about the teammate, but it just says there's a teammate that's yeah, that's kind of what I'm working on here, because they want to be able to know, yes, where their teammates are, but since they're not actively supposed to engage or talk to. They have to maintain radio silence. So, I can't say, okay, Joe, let's go this way. They're not supposed to do that. Basically, once they hit the ground, it's like, I'm one man or woman. I'm one man or woman, and I need to get to this. That's my job. But at the same time, they kind of want to keep an awareness. So if I reach my goal and Bill and Bob haven't arrived yet, I can't do anything. I have to wait for them. So it's nice to know what they're doing, if they're running in circles or if they stop moving. I need to know that. Or if they're panicking, I need to know that.
Excuse me, is that all that communication's peer-to-peer, or you're assuming you have some sort of network?
There's no network cut. So
So
this
it's
is all offline.
It's
Yeah.
all peer-to-peer using Wi-Fi and
Yeah,
support?
so it's an ad hoc Wi-Fi network that's being generated by the ruggedized computers and the Wi-Fi component attached to them. We're creating a Wi-Fi network that never gets connected to. It just turns on and off.
Right, that's the beacon operation, but you said that two Android phones also communicate.
Oh,
with
sorry,
each
yeah,
other.
same thing. Same method. So it's basically all done all done by tethering, and so it's turning on its Wi-Fi on and off, and it's just broadcasting its location, and that's pretty much it.
Presumably, you, as much as possible, want this to be covert, that you have these beacons sort of communicating where they are. Now, you said the actual data is encrypted.
No. I'm sorry, the operation itself is not covert. That's kind of why there's a time sensitivity to it. Basically, there's 1,000 guys jumping out of a plane. People are going to see that. The danger comes in them basically running around for 2 hours trying to find out where their equipment is. So the whole purpose of this system is to minimize the amount of time that they're running around. So people, if anyone does, is in close enough to recognize the symbol or pick up the signal, basically we want to make it difficult for them to, one, identify that, okay, there is a signal, even though it's kind of turning on and off, there's something there. Once they identify that, they'll have to decrypt it, find out, all right, what's the...
Oh, well, I guess that was my point, because they'll be able to just use direction finding. They don't really need to decrypt the GPS coordinates as such, just having the people communicating.
Yeah,
So,
if
yeah.
you did kind of like have a car or something, and you're driving around to see if the signal getting stronger, I mean, ideally that should still take you longer than 8 minutes, we hope. So it's like if you guys are running around for long enough for them to be able to find the signal and find out where you guys are, then you were out there too long, something's wrong. So yeah, that's the goal, is to limit that amount of time, not necessarily to hide that they're there, because everyone knows that they're there once you see out of a plane. Find your equipment and don't be there by the time other workers get back.
Yeah.
Okay.
So what are the next steps in terms of future experiments you're going to do?
So the next step for me, my colleague is working on the haptic vest. The next step for me is to create a visualization of the stress, non-stress state that we're currently monitoring, and then to be able to tailor the system for the group of firefighters that we're working with and rescue aid workers that we're working with at that are training at Disaster City. That's kind of our next phase, but somebody's gonna that over after. That's another big thing, but that's our goal.
And you brought the EEG equipment with you, didn't you?
I did. So if
So
anyone
let's try
wants
it.
to be tortured, no, not tortured, contribute, I would love to collect some data. I might make you watch it. No, I won't make you watch it. There's lots of pictures, lots of really.
Any other questions? Great, okay, well, thank you again. Thanks, Dan. That's great.